Okay, so where we left off at the end of chapter 8 was this sort of decision-making point where we said, well, when do we need to use systematic treatment of equilibrium, and when can we get away with simple assumptions? And it's not always a cut and dried answer, but when we're talking about at least acids and bases in solution, the criteria that we discussed right at the end of the chapter 8 videos was when the concentration of those strong acids and bases is in the range of 10 to the minus 6 through 10 to the minus 8. So low concentrations, right? This is in molar. So that's anywhere from 1 micromolar to 0.01 micromolar. So really, really low concentrations of H+. That's when it becomes relevant. When we say that's when it becomes relevant, what we really mean is that not only can we consider simply the concentration of protons from the strong acid or the strong base, but we also have to consider the protons simply coming from the dissociation of water itself. And as I alluded to at the end of that video, the reason for this is because we know that the equilibrium constant for the dissociation of water is Kw, which is equal to the product of the ion concentrations, H plus times OH minus, and that's equal to 10 to the minus 14, which means at equilibrium, each one of these concentrations, and by equilibrium I mean when there's nothing else in the system, so you just have H plus and OH coming from water and nothing else, then those two concentrations are 10 to the minus 7 molar. So it's when the concentration of protons coming from an acid or a base being added to the system, when those concentrations are on the order of that you get from simply the dissociation of water, that's when we need to consider a systematic treatment, because now we have essentially a common ion problem where you've got some amount of H plus and hydroxide and some amount coming from another equilibrium. So that's going to shift the equilibrium, and to account for that, we're going to have to treat it systematically. So let me give you a quick example of what that might look like here. Okay, so the dilemma that we have is this question. So what is the pH of an HCl solution that's equal to 10 to the minus 9 molar in water? And at first glance, you may look at this and have no issue with it. And that's totally fine, because your instinct would say, well, HCl is a strong acid. What do we know about strong acids? Well, strong acids mean that the equilibrium lies dominantly towards products, which means that we can assume that HCl is just 100% dissociated. So whatever concentration of HCl we have, in other words, since it's 1:1, that's the concentration of our protons in solution. And for that reason, if the H plus concentration from HCl is 10 to the minus 9 molar, then to get to pH, we simply just need to take the negative log of this value. So if I take the negative log of 10 to the minus 9, so pause the video, take that for a second because I don't have a calculator on me right now, so compute that value really quickly. You probably didn't need a calculator for that, I was just trying to get you to pause the video there. That gives us a value of 9. So even at this point, you may just sort of go about your daily business had I not sort of primed you for something awkward here as a dilemma. What's wrong with this picture? You've got a beaker that's pure water, right? And then to that, you add some small amount of a strong acid. And what you concluded was that the pH of this system is basic. How is that possible? Significantly more basic. It's 100 times more basic than pure water. So how is it that you added a strong acid and you yielded a system that's at 10 to the minus 9? This would probably be better off if I illustrated this at, this could have been at 10 to the minus 8. And in that case, this would have been a pH of 8. This would better fit within the window here, but 10 to the minus 9 is comparable to. But it still illustrates this issue, right? How is this even remotely possible? And well, it's not, right? The reason here is because you're dealing with really, really low concentrations of the strong acid, such low concentrations of the H plus in solution that the actual concentration coming from water dissociation itself, of course, is considerably higher, on the order of 10 to 100 times higher in the case of this. And so if we neglect to consider the dissociation of water in this case and the treatment of this monoprotic acid, then we're gonna get a nonsensical answer. And so this dilemma, we could easily do it at 10 to the minus 6 range too. We could do it with KOH. I mean, we could do a strong base or strong acid. Either way, in the range where you're plus or minus 1 order of magnitude in concentration away from 10 to the minus 7 molar, that's when it becomes especially relevant. Sometimes even out here, if we're trying to keep more than 3 significant figures, then it becomes really important. So let's walk through the basic systematic treatment of this problem then. Alright, so first step is just going to write out the relevant reactions here, and we've already sort of discussed these. We've got obviously the dissociation of the strong acid, which is HCl. That has a really large Ka. It's not going to be important that we write that down here right now. We could look it up. It's on the order of 1,000 or 10,000, I can't remember. And then we also have just the reaction of water with itself, which we call the dissociation of water into protons and hydroxide, and that has its own equilibrium constant Kw of 1.0 times 10 to the minus 14. So we can craft a charge balance pretty quickly here. So there's not much going on in this system, so the only positive ions we have are H+, and the only negative ions we have are OH- and Cl-. So we set those concentrations equal to each other. There's probably a couple different mass balance equations that we could compute, but if we go back to the original constraints of the problem, we are given a concentration, which was 10 to the minus 9 for our HCl. We don't necessarily know, so if HCl concentration is equal to 10 to the minus 9 molar, we don't really know what the concentration of H+ is from that, because that's going to be a contribution from water itself, but we could conclude that chloride is only being added from HCl, so that has to have a concentration that is consistent with 10 to the minus 9 molar. So that looks like a simple mass balance, but it's true, right? It tells us one of our variables, one of our unknowns, is equal to a constant, and that is an equation. All right, so just writing up the two equilibrium expressions for the two reactions that we listed in step 1. So we have the dissociation of water, and we set that equal to its equilibrium constant, which is Kw. We have the dissociation of HCl. We set that equal to its Ka, which I looked up. This Ka will differ wildly. It's difficult to measure, but it's on the order of 10 to the third or 10 to the fourth. But in the value that I'm looking up, I get 1.0 times 10 to the third. Okay, so the last step here then would be to count up our unknowns and count up our expressions and see if we have enough to solve this via substitution. So we can look through these. We've got H+, that's 1, OH is 2, Cl is 3, and then technically HCl, which we're not really interested in computing, but it is an unknown, would be 4. We've got a charge balance, a mass balance, and 2 equilibrium expressions. So 4 and 4 makes this solvable. So as always, like when you're doing algebraic substitution, you can go about it a million different ways. So there's no absolute. I'm just showing you how I would have gone about this. So I'd start sort of simple. That's always easy. So I start with the mass balance. The chloride is equal to 10 to the minus 9, and then I'm going to take that chloride value, or that 10 to the minus 9 value, and I'm going to pop it in for the chloride. That came from our charge balance expression. That gives me H+ is equal to hydroxide ion plus 10 to the minus 9. So I'm going to take that now, and I'm going to substitute that in, or actually I'm going to rearrange my Kw expression. I'm going to substitute that in for hydroxide ion. So that gives me H+ is equal to Kw over H+ plus 10 to the minus 9. So you can see the red arrow. I'm just swapping out that for hydroxide there. So that gives me this new expression here, which now has H+ in terms of H+. And constants, which is what we're looking for. So last step here is just, you don't have to do this, but I just think it's easier to see the values here. So I just let that H+ be equal to X. I just collect like terms, so just collect the H pluses. And what we get as X squared is equal to Kw plus 10 to the minus 9X. Rearrange that, solve for set to 0, so you get X squared minus 10 to the minus 9X minus 10 to the minus 14, all of that being equal to 0, which now is in the form to be solved by the quadratic equation. Alright, so I just threw up the quadratic equation. If it's been a while since you've seen it, you saw it in a previous video, but I didn't explicitly solve for that. So it's minus b plus or minus square root of b squared minus 4ac all over 2a. And remember, those variables, the a, b, c, come from the coefficients that precede each of the values in the quadratic, or in the actual quadratic equation, in the form of the quadratic. So in this case, a would be just 1 because it's in preceding the x squared, b would be this 10 to the 9 value, and c would be this entire value, this negative 10 to the minus 14. So I'm going to throw those in, substitute those into the actual quadratic equation, and that's going to give me two values because of the plus or minus, and then let's see if we can make sense of those two values. Just as an aside, I don't care how you solve the quadratic equation in this class. I'm not really evaluating based on your algebra techniques. It's just an assumption that you know how to do that. But I also understand that transcription errors abound when you're solving this sort of thing by hand. So you can solve it by hand, totally fine. You can solve it with a calculator if you've got a scientific calculator that has a functionality that allows you to solve quadratics directly, or you have a program that allows you to do that, or you can use online quadratic calculators, which is what I often use because I'm lazy. Whatever you do, that's totally fine. If you're doing this for a quiz or exam, I'm not going to be able to give you partial credit if I can't see your work, if you made a mistake. So whatever you do, be clear that I can only grade what I see. So if you're going to use some digital methodology to produce a value, totally reasonable, make sure that that value is right, because if you made some error transcribing it digitally, I don't know that, and so I won't be able to deduce that. So you're always going to have the quadratic equation as something I'll give you on this. Likely most of your quizzes are going to be done in groups, and your exams will probably be open book. At this point, as I'm recording this, I don't really know, but probably that's going to be the case, in which case I often also allow you to have a computer with an Excel workbook open, which means that I'd be happy if you also used a quadratic equation computer either in a browser form or on a calculator, whatever gets you the right answer. I'm less concerned about your algebraic skills, because you're always going to have those resources in real life, like me. And then I just don't spend the time doing this by hand. I just punch it into a calculator or put it online. Okay, if we solve that, what do we get? Well, we get a value of 1.005. This is the only real value of x that we get. 1.005 times 10 to the minus 7. Remember, that was equal to h plus. So the negative log of this is what's going to give us the pH value. And this is where, as I'd mentioned a million times already in this class, the level of accuracy that you use and the models that you use to calculate values is going to depend on how much error you have in those numbers to begin with. If this case you're keeping all four of these significant digits, then you can see that it's only in the fourth digit where this manifests, where the actual systematic treatment manifests. Because really what you're seeing here is the pH is largely dictated by the first reaction, by water itself, because the H plus coming from HCl was at the 10 to the minus 9 range. So it was pretty inconsequential. And so if we just assumed that, well, concentration of HCl is so low that the H2O dissociation is really going to dictate this, what we would have assumed then was that the concentration would have been 1.000 times 10 to the minus 7. And so the difference here is in that fourth significant digit. If our HCl concentration was 10 to the minus 8 instead of 10 to the minus 9, we would have seen that in the third digit instead of the fourth digit. So it makes sense, hopefully, to you that really it depends on how many digits you're going to be able to conserve, how and whether you need to conduct this type of systematic treatment. So we take the negative log of this value to get a pH. What my calculator gives me really quickly. Let's pause this. I get 6.9978, and then I subscript the 3 as insignificant, and that's assuming that I'm keeping all four of these digits. So if I keep all four of these digits, 1.005, remember those are all significant because that's a value, not a logged value. But once I log that value, then that 6 here is not significant. That's just a 0 placeholder. And so I take all four of those original digits and I put those out here. And so I have 6.99783. Those are all significant digits. Those are all real values, which would differ from 7.0000. And notice how if I would only have been able to conserve 3 digits, then this whole thing would have rounded up to 7.00. So it's important to note what the impacts of these are. What I'm giving you here is the tool to do this the right way every time, but as I've said a million times, my goal is not for you to do it this way, the most cumbersome way every time, because that's not going to be the most useful utilization of your time and resources. What I want you to start to think about is the chemical intuition. What do I have in solution? What else is in solution? And how should I start to think about solving this? So this is how you'd solve it for a simple strong acid monoprotic system.